Hello, this video is going to be a summary of the best results I've achieved so far regarding designing impulse drives and making the theory of Tetryonics computational. If you cumulatively integrate a sinusoidal acceleration twice, you will create a net average velocity and displacement despite there being an average acceleration of 0. From these cases, we can see that if you want to increase the average velocity, you must increase the magnitude of the acceleration and not its frequency. A moving mass that has had its momentum constrained to follow the path of a circle will experience a sinusoidal force created by whatever is constraining its momentum to the circular path. A corresponding equal and opposite reaction force will be exhibited by the mass onto the path. This is usually described as a centrifugal force, which is proportional to the tangential speed of the mass squared, the magnitude of the mass, and inversely proportional to the radius. If we had a revolving mass and increase its tangential speed at exactly the start of every second revolution non-linearly, we would get an acceleration and displacement response like this. We can see that we have technically created an acceleration because the average velocity increases and the displacement is non-linear, even though the acceleration ay still has an average value of 0. This system has an odd characteristic, however. Since we had to increase the magnitude of the tangential speed of the mass non-linearly, this system suffers from diminishing returns on output acceleration versus input energy. To achieve a constant acceleration, we have to add energy into it at an increasing rate instead of a constant rate. Also, because there is still no average acceleration, this trick only works in the absence of any external forces. For example, you could not use it to overcome gravity, but you could create an apparent acceleration across a flat, low-friction surface. In order to overcome external forces, the acceleration needs to definitively have an average value. There are two ways we can achieve this: by adding a DC offset to a sinusoidal function, which would be equivalent to simply having an external force act on the system, or by bending the shape of the sinusoidal function, such that its peaks and valleys don't create the same area between them and the zero axis. An example function of this is the function for describing phase modulation. Another way we can force the acceleration to have an average value is by being more careful in how we force the tangential velocity to change along the circular path. If we pulse the tangential speed of the mass such that it has a greater velocity on one side of the circle than the other, we create an effect where the mass accelerates while traversing left, then deaccelerates while traversing right. Both of these changes in momentum create a reaction force pointing in the same direction. The magnitude of these reaction forces depends on the rate of change of the tangential speed, not on its instantaneous magnitude like the centrifugal force does. If we are free to assume any continuous speed we want over the length of the circle, we could potentially overpower the centrifugal reaction force. We also need to employ a strange trick here, whereby starting with an assumed speed as a function of position, if we want to integrate the reaction force on the circular path with respect to time to discover its resulting net velocity, we have to first compute what time is as a function of position, as time is no longer an independent variable. When we do, we can see that time is no longer linear and that this will change the outcome of integrating the reaction forces. The top graph here is the instantaneous x-component of the mass's tangential velocity and its associated x-component of acceleration, which has been scaled to simply be easier to see. If we cumulatively integrate this acceleration with respect to nonlinear time, we end up with the result that the circular path acquires an average x velocity and an average x acceleration. There are many different ways of constructing other paths that are not circular which also have these same properties. If we take the previous equation we discovered for step displacement via cumulatively integrating sinusoidal acceleration, and we normalize it such that its step values are multiples of pi and pi over 2, then we use this as a reparametrization for curvature and put it into the parametric equation for a circle, we end up with a triangle. An interesting note for much later is that this same equation that describes step displacement has the exact same algebraic form as the area that a triangle projects into a plane as the triangle rotates. We can employ a similar strategy to the pulsing of the speed of a circularly revolving mass to this triangular path and achieve a similar result. If we assume that a mass traverses this triangular path, it has the instantaneous tangential x and y velocities as shown below. The change in these velocities will create reaction forces on the path against whatever is constraining the mass's motion to remain on the path. If the path is free to move, and the mass has more kinetic energy than the path, the mass will transfer energy into accelerating the path via these reaction forces. If we further assume that the mass always has more kinetic energy than the path, we can cumulatively integrate these reaction forces to discover the paths resulting in motion. This is a very important assumption because it implies that we are assuming a velocity across the path that is a function of position, like we did for the circular pulsed speed case, which means time is not an independent variable here either. It also implies that in the path's rest frame of reference, this velocity function does not change. In order for the assumption that the mass always has more kinetic energy than the path to be true, the path also has to tangentially accelerate the mass along it in such a way that it replenishes any energy lost by the mass to accelerating the path. Here we see the result of cumulatively integrating the tangential and perpendicular accelerations according to nonlinear time, where the tangential accelerations correspond to accelerating the mass parallel to the path, and the perpendicular accelerations correspond to constraining the mass's momentum to the path. We can see that the perpendicular reaction forces have an average value that is changing, whereas the tangential reaction forces have an average value that is not. These integrations were done independent of each other to demonstrate this fact, as over the current domain, the effect of the perpendicular reaction forces is negligible in comparison to the tangential ones. This desired effect is present for this path, but very small in magnitude. There is an even simpler example of a path that will produce the desired effect, where it is obvious that it should, subject to our assumptions. If we construct a path like so, where the blue section between x equals -1 and 0 is y equal x to the 8, and the red section between x equals 0 and 1 is x squared, and these two sections are joined together by a circle with a radius of approximately 1 that is tangential to the end of each curve, it is trivial to demonstrate that the valuation of integrating the derivatives across the x domain cannot be 0. Furthermore, it is clear that this integration for the second order derivative is greater than for the first order derivative, where the second order derivative would correspond to perpendicular reaction forces experienced by a mass traversing this path, and the first order derivatives would correspond to the parallel reaction forces experienced by a mass traversing this path. Because we could have chosen any even powers that are different to define this curve, we can see from this example that there is at least one infinite class of curves that have the property that their derivatives have average values along particular directions. This is the result of the same cumulative integrations as we did for the triangular path. We can see that the y velocity resulting from cumulatively integrating the perpendicular reaction forces around one traversal of the path is 0.26, as compared to the triangular path of 0.05 after 3 traversals. By choosing a better geometry for the path, we improved the magnitude of the effect by about 15 times. The graphs have odd-looking discontinuities in them because the way the curve is defined isn't perfectly continuous. We can see that these discontinuities will cause the main integral of interest to undershoot its ending value, so a final y velocity of 0.26 is only an approximation that's a bit lower than what the actual value would be. We can employ a general strategy for finding curves with this property. Start by assuming an acceleration over time for a particular direction. Integrate it twice with respect to time to find position as a function of time along that direction. The specifics of the final two steps are not well defined, but the key insight is to realize that this position as a function of time is not the closed curve in its rest frame. It is the sequential position of a mass traversing that closed curve as the curve itself displaces. You have to find the function that describes the curve's velocity through time and subtract it from the first integration of your assumed acceleration before you integrate it for the second time. Then you need to discover a periodic function for the position in time over the perpendicular direction such that you can close the curve. The specifics of this algorithm are not well defined because I tried this for the phase modulation graph and was simply able to guess what the other two functions should be with minimal trial and error in order to close the resulting curve. These are the results of the same cumulative integrations of the curve's perpendicular and parallel reaction forces. We can see that for the y velocity, the end value is about -1, 4 times better than the previous curve and 200 times better than the triangle. It is possible to take a closed path and find an equivalent circular path of varying speed, and possibly one that retraverses previous arc lengths, depending on the complexity of the first path. The algorithm for doing so is simple. Just map every point on the first curve to a point on a circle where the tangent vector of the first curve is parallel to the tangent vector of the circle, and make the corresponding speeds equal. Now you have a circular path of varying speed where the speed is a function of position. You employ the same trick regarding computing time as shown previously. This all means that any closed curve that effectively employs a spatial control scheme on the parallel and perpendicular reaction forces that a mass traversing the curve would experience can be made equivalent to a temporal control scheme on a circular path. To recap what we've constructed so far, there are closed curves whose tangential derivatives have average values along particular directions. This means that a mass constrained to traversing these curves for finite total energy will oscillate through space by passing energy back and forth between the mass and the curve via reaction forces, creating an average velocity for both the mass and the curve, but no average acceleration. If we are able to assume that the mass always has more kinetic energy than the curve, then the curve will experience an average acceleration. This assumption requires us to constantly accelerate the mass at an increasing rate to achieve a constant acceleration for the curve. Closed curves of arbitrary geometry can be made equivalent to circular curves with varying speed. This fact is useful for satisfying the assumption that the mass always has more kinetic energy than the curve. If we apply a force coupled to a radial system, there is no net linear reaction force. There is a reaction torque. Because there is no net linear reaction force, then the reaction from accelerating the radial system to rotate faster cannot interfere with the linear acceleration of that system's center of axis. We can potentially satisfy our assumption of the mass having more kinetic energy than the path by applying an increasing torque to it in order to scale the mass's assumed tangential velocity for an equivalent circular path of varying speed. This would allow us to create what I call an impulse drive, an apparently reactionless drive system. This drive was inspired as an application of the theory of Tetryonics, an alternative theory of quantum mechanics as well as a theory of everything that was created by Kelvin Abraham. A working impulse drive would simultaneously be economically useful and provide evidence that Tetryonics is correct. But to see how that is the case, I first have to give you a very quick and simplified crash course on how Tetryonics works. Tetryonics makes a few axiomatic assumptions about energy, and one of its crowning achievements is that doing so allows you to derive the periodic table of the elements. We start by assuming that energy has a physical geometry. Energy comes in two different discrete units, or quanta, that have a 2D equilateral triangular geometry that is separated into four different components. Two diamond-shaped electric field components, which are on either side of the triangle, and two different pairs of north-south magnetic field components also located on either side of the 2D triangle. These quanta are assumed to be perfect self-inductive loops. The electric and magnetic fields they are comprised of periodically induce each other without loss. This self-induction can be modeled as a physical rotation about their center axis, which also means that there are two separate types of quanta. Positive quanta, which obey a right-hand rule, where your thumb corresponds to the electric field, and your fingers the magnetic field and direction of rotation, and a negative quanta, which obey a left-hand rule. In addition, these quanta have mass and velocity associated with them, with their velocity vector pointing from the base of the triangle toward its tip. Quanta join together to create kinetic electromagnetic fields, or chem fields. Chem fields are a larger equilateral triangle made out of smaller equilateral triangles. Chem fields rows increase and decrease in sequential odd numbers of quanta. You get +1 net momentum for every row, and there is always a total square number of quanta in a chem field. You get diminishing returns on net velocity for each row of energy added because the amount of quanta required to complete each subsequent row increases. In this theory, energy is quantized, but you can continuously rescale every component aspect of quanta. Thus, quantization has become a geometric constraint. Quanta join to create chem fields by inductive coupling. The entire chem field behaves like a scaled quanta. It has the same sign of net polarity of electric and magnetic field components, and their mutual induction can be modeled as a simultaneous rotation of the entire chem field as well as its individual quanta about their respective axes. Look at the red and black triangles at the tip of this triangle. Cross your wrists and curl your fingers according to a right-hand rule and a left-hand rule. Your fingers curl the same way. The magnetic components associated with your fingers are reinforced, while the thumb-associated electric field components and momentum is cancelled. This is what is meant by inductive coupling. Model static electric fields by doing the opposite. Imagine two back-to-back right-hand rules. The curling fingers cancel in addition to the thumbs. You can use all possible combinations of left-hand rule and right-hand rules being paired together as well as overlapping with another pair to recreate electrostatic and magnetostatic interactions. Electric and magnetostatic fields are diamond-shaped. Momentum is not uncancelled to create the forces associated with electrostatic interactions without overlapping one diamond pair with another. In Tetryonics, forces are created by overlapping geometries. You can also cancel momentum by folding a chem field into a tetrahedron. This results in four types of tetrions, positive, negative, and two different configurations of neutral. Tetrions form the basic building block for constructing all matter. By an unfortunate coincidence, they can have the same charge-to-mass ratio as different flavors of quarks, and so are indistinguishable from them via ordinary detection methods in particle colliders. Tetrions join together via electric and magnetostatic attraction between their faces to create larger subatomic particles. The net charge of matter is determined by the net polarity of its outward-facing fascia. Subatomic particles, like protons and neutrons, can be constructed from tetrions and can also be joined together via electric and magnetostatic attraction between their faces. Because of the inherent restrictions of their own geometry, they can only join together in a very specific pattern. By coincidence, this recreates the periodic table, even down to the progression of electron orbitals. Tetryonics is far from a complete theory. Its biggest issue is that it only qualitatively describes phenomena. The theory would be more useful if it was capable of making quantitative predictions. Impulse drive arose out of my attempts at constructing a time-dependent mathematical model of quanta. Pure sinusoidal acceleration with constant total energy is a partially complete, one-dimensional time-dependent description of a quanta. Creating an impulse drive capable of acceleration should also give you a partially complete model of how forces between chem fields should work in Tetryonics. The model will still only be one-dimensional, time-dependent, whereas the complete model of quanta and forces between chem fields should be a time-varying vector field that is a solution to some kind of partial differential equation, at least over 3 dimensions. If we displace 2 points that are circularly revolving in opposite directions according to the stepped displacement model we started with for impulse drive, we can see that these points trace throughout space a similar geometry to the repeating diamond columns of a chem field. We can also see from the examples that there has to be a specific relationship between A, W, and R for the resulting geometry to remain regular. There's a way we can transform the 2D geometries we've constructed so far into being 3D and enforce a constraint of conservation of energy on them. We can define a composite system, linear kinetic energy and radial kinetic energy, that oscillate out of phase with each other, but whose total energy sums to a constant value via sinusoidal identities. Furthermore, if we assume that the energy within each subsystem is sinusoidal, we can show that the corresponding equation for energy can be modified to be equivalent to the cumulative integration of sinusoidal acceleration. Cumulatively integrating velocity again gives us the familiar stepped displacement graphs of impulse drive. Both subsystems oscillate, the velocity is what is changing in the linear system, and the radius is what is changing in the radial system. If we trace out the path of rings of points subjected to this constraint, we get these 3D graphs. They're also very similar to the diamond columns of chem fields in Tetryonics. If we want to try to construct a model for individual quanta specifically, we can surmise what we must do is somehow get rid of half of the diamond geometry and collapse the result together. We can actually derive this desired result from a mass revolving in a circle subjected to a few constraints. We start with the familiar parametric equation of a circle and its corresponding second-order derivatives. If we cumulatively integrate these second-order derivatives, we end up with the tangential velocity components around the circle. Not setting the constant of integration to 0 implies a change of reference such that this constant of integration corresponds to the average velocity of the circle's center axis. If we cumulatively integrate again, we end up with the general position of the mass throughout space. By definition, we don't want the circle's axis of rotation to have an x velocity, so we set Cx equal to 0. We want our system to be comprised of two subsystems, radial and linear kinetic energy, so we reparametrize Px like so, such that it becomes a radius that is never negative. We want the energy of our two subsystems to be out of phase. If we take the derivative of Py, the velocity and radius are both proportional to cos, making the energies in phase. To fix this, we phase shift r by pi over 2. If you want to make sure energy is actually conserved, we also have to go backwards and show that it is constant. We have a problem here in that we cannot simply square and add these two equations without ending up with a time-varying term. The solution is to separate the terms corresponding to our two frames of reference, a mass revolving in a circular path and that path's center of axis translating, and conserve the energies corresponding to each frame of reference separately. By doing so, we end up with two terms that follow the algebraic forms of radial and linear kinetic energy that have a constant sum over time. If we plot out the position of two mirrored points according to the derived equations, we get repeating triangles. This is effectively a 2D slice of an oscillating ring whose radius and velocity oscillate out of phase. It is advantageous to define r and w of this composite system to be inversely proportional to a because this will allow quanta to recreate aspects of relativity. A corresponds to the average displacement of the oscillating ring that traces up the triangular geometry. If A increases, we would like the physical size of the resulting geometry to decrease, thereby creating wavelength contraction. We would also like the internal frequency of the geometry, or rate at which it cycles, W, to decrease, thereby creating time dilation. In the second picture, we can see the result of wavelength contraction. However, the equation graphed here has been modified to effectively set the average velocity term of the ring to 0. We can see that in the third picture, if we don't do that, the apparent wavelength of the geometry actually expands and it is no longer triangular. This is because the classical definition for frequency of repeating units passing by a point is something very different from the internal rate of cycling or self-induction of quanta in Tetryonics. The comparative rate of cycling of the quanta is getting slower because W is decreasing. In a rest frame of reference, the quanta's physical size is becoming smaller because R is decreasing. But we can show that the classical frequency of the higher energy quanta is increasing. If we have a checkerboard that rotates as it translates, then from a fixed external perspective, its checkers decrease then increase in size. Forces in Tetryonics are created by an overlap between separate geometries. If both geometries rotate, they can overlap out of phase, and the amount of effective overlapping area is thereby smaller than it otherwise could be, and you would measure a weaker force, and thereby less energy than the geometry actually has. If geometries of different energies rotate at different rates, and if one has far more energy than the other and thereby rotates far slower, then it effectively undergoes no rotation as it overlaps with the lower energy geometry, and the lower energy geometry will experience a greater transfer of energy into it from the larger one. In the standard model of physics, we know energy is proportional to frequency, which allows us to surmise a few things regarding Tetryonics. Firstly, the internal rate of cycling of geometries is a completely different property than their apparent classical frequency. Forces are created not just by overlap in space, but also in time. And finally, that the energy transfer mechanism between geometries is dependent upon energy density in time as well as space, and not just on the total energy. To review what we've done so far, with two mirrored masses revolving around circular paths, we can cumulatively integrate second-order derivatives of position twice with respect to time to get stepped displacement. This second-order cumulative integral of sinusoidal acceleration can be normalized a particular way to define stepped curvature. Reparametrizing circles in terms of stepped curvature, whose steps are increments of pi and pi over 2, creates triangles. An alternative way of defining triangles involves periodic displacement and expansion/contraction of a ring. The position of the ring throughout time uses the same algebraic form for step displacement, and the derivative of step displacement for the radius of the ring. Because the magnitude of the radius of the ring and the magnitude of the ring's velocity are out of phase by 90 degrees, they can be separated into different terms that satisfy conservation of energy. This defines a composite system of linear kinetic energy and radial kinetic energy, where the energies are the sum of periodic terms that are out of phase with each other, as well as constant terms. The total energy of the composite system over time is constant. This composite system is subject to wavelength contraction and time dilation, and the apparent classical frequency of the system extended in periodicity through space is a very different property from the rate of its internal cycling. However, to constantly add energy at an increasing rate into only the radial system such that you satisfy the constraint that the energy of the radial system is always greater than the energy of the linear system, the radial system would continually transfer some of its energy into the linear system. Focusing on only adding energy into the radial system allows you to add energy via a pure torque from a force couple, creating a reaction torque in the process. This reaction torque will not affect the net average acceleration of the linear system if the radial system has been mirrored the same way the oppositely rotating circles have been in the first figure. Doing this would allow you to create an effectively reactionless drive system. There are infinite classes of closed curves that have average values for the tangential derivatives along particular directions. Some of them are better at having this property than others. These curves are demonstrations that if one could assume a constant offset in energy between a mass traversing one such curve and the translating curve itself, then the energy will transfer into accelerating the average velocity of the curve. Mirrored 30, 60, 90 special triangles are one such curve. Two placed side by side create an equilateral triangle like Tetryonics uses as a quantum energy to describe everything. These classes of closed curves can be made equivalent to a circular closed curves with varying tangential speed, which would more easily allow one to create a device that scales this varying tangential speed via an applied force couple. At this point, we basically have a 1D time-varying model for a quanta and a description as to how it arises. But a quanta is not the same thing as a chem field. We need to somehow incorporate spatial periodicity in other dimensions. We need the composite result to be the solution of some kind of partial differential equation in order to describe how chem fields are created as a superposition of interacting quanta, and how quanta or energy can be transferred between chem fields to create acceleration. A useful practical application of a PDE model as to how chem fields behave under acceleration is an impulse drive. A final hurdle to overcoming regarding making an operational impulse drive is discovering how to input energy into one half of the composite system such that the reaction force from doing so does not interfere with creating an average acceleration. I hypothesize that if you can construct a way of accelerating the radial half of the system such that the reaction force from doing so is a pure torque, then you can create a working impulse drive by mirroring the system across the same frame and constantly increasing that applied torque. I'm currently working on experiments to demonstrate this. I'm also currently doing theoretical work regarding how to extend the current model of impulse drive to a vector field description, as well as discovering partial differential equations that it is a solution of. That's all for today. Thank you for watching.